we can further simplify our expression by applying the following claim. It claims that if f is a 2-pi periodic function, then the integral from a up to a plus 2 pi of f is equal to the integral from 0 to 2 pi of f for all a inside R. And that means if our interval of integration has a length of 2 pi, then its integral is indeed equal to the integral from 0 to 2 pi. And how can we prove so? Well, we let n, which is an integer such that n times 2 pi is inside the interval a to a plus 2 pi. And we claim that this integer exists because the length of this interval is equal to 2 pi. And so we can divide our integral into two parts. The integral of a up to a2 pi can be split into two parts. The first part is a up to n times 2 pi, and the second part is from n times 2 pi up to a plus 2 pi. And we call this integral I1 and the second integral I2. And we apply the change of variable x equal to 2 pi plus y on I1, and you can prove that it is equal to the integral from a plus 2 pi up to n plus 1 2 pi of f plus the integral of f from n times 2 pi up to a plus 2 pi. And you see that these two intervals are connected to each other, and therefore it is equal to the integral from n times 2 pi up to n plus 1 times 2 pi of f, and apply another change of variable z equal to y minus n times 2 pi, we get that it is equal to the integral from 0 to 2 pi of f, and we are done with the proof of the claim. And therefore, from this claim, we see the following corollary. It says that if the length of the interval right here is equal to 2 pi, then the integral are the same. This is because both of them are equal to the integral from 0 to 2 pi. And therefore, remember our expression in the previous page. It says that the partial sum can be expressed in the form of the integral from negative pi plus x to pi plus x of dnz fz plus x. And notice this is a 2-pi periodic function because dn is a 2-pi periodic function as well as f. Also notice that this thing has a length of 2 pi, and therefore it is equal to the integral of another interval which has a length of 2 pi, and therefore it is equal to the integral from negative pi to pi of dnz fz plus x dz. So, in conclusion, we say that the partial sum of f up to the nth order is equal to the integral from negative pi to pi dnz fz plus x dz, where dz is equal to sine n plus 1/2 of z divided by 2 pi sine 1/2 of z if z is non-zero, and it is equal to 2n plus 1 over 2 pi if z is equal to 0. So we are done with expressing our Fourier series in a closed form, and in the next video we will continue on the properties of the dn function, and see you in the next video.